Okay, so in this section, I'd like to define what it means for a sequence to approach plus or minus infinity, and then also adapt some of the previous limit theorems for sequences that approach plus or minus infinity. I want to warn you, and the book gives this warning as well, that just trying to directly apply the theorems like 9.1 through 9.6 or whatever, the ones we already proved, for sequences that approach plus or minus infinity is not a good idea. First of all, the arguments we made there just don't apply to sequences that approach plus or minus infinity. But second of all, you'll run the risk of accidentally applying one of those theorems when there's an indeterminate form. So for example, the product theorem, right? If you have one sequence that approaches infinity and then the other one approaches zero and you multiply them together, how do you tell what happens? You can't really. So we rephrase these theorems for sequences that approach plus or minus infinity to be very careful, okay? So first, let's actually define what it means to approach plus or minus infinity. And we still call this divergence, even though we say the limit exists in these cases. But yeah, so we'll say definition. We say, okay, let me make sure I get the notation right here. So for a sequence Sn, right, we write limit of Sn equals positive infinity if for any m, I'll just say there exists some n such that for n greater than n, we have Sn greater than m. Okay. Note also that, right, yeah. Note that the book for some reason says for any m greater than 0, okay? We don't need that. It's like completely unnecessary to require m to be greater than 0 here. It doesn't change the definition really. Like they define the same concepts. I don't understand why the book put the greater than 0 thing there. It does nothing. So yeah, basically this is the definition in sort of a cleaner form. And so yeah, just notice how similar it is to the definition of convergence. So in this case, we say the sequence diverges to infinity, okay? So yeah, I'll do a recap of the terminology later after we've sort of finished talking about the definition. But yeah, notice that the structure here is fairly similar, right? It's saying that like someone can hand you a certain number, right? And then you have to find a cutoff in the sequence so that after that point, basically, a certain condition having to do with that number is satisfied. And this has to be true for any number that you can start with, right? Before it was epsilon, right? And epsilon was supposed to be like the tolerance, how far away you were allowed to be from the limiting value, right? Now, instead of an epsilon keeping us close to a limit, it's an m, which is just supposed to force the values in the sequence to get larger and larger, basically. So like you can pick whatever m you want, and then you can find a place where the sequence always stays above that value m. That's what it means to approach positive infinity, okay? There's a totally like mirrored definition for negative infinity. I can literally just change a few things here, and yeah, I think I literally only have to change 2 things. And again, they put like less than 0, yeah, and that's just not necessary. So just ignore that. Yeah. So this is what it would be for negative infinity, right? Very similar, just a couple things flipped around. So now let me just like quickly recap what terminology we have so far, okay? So there are sort of 3 situations. So recap of terminology. Right, so we can have Sn converging to a number S, which is real, right? This is where Sn converges, right? We can have Sn going to plus or minus infinity. This is Sn diverging. And this, right. So yeah, and then we can have Sn just diverges completely, right? Where it literally just has no reasonable behavior, no consistent behavior in any way, right? It just like, it's all over the place. That's the last thing. This is the most fundamentally, in a way, like diverging to plus or minus infinity is kind of still closer to being like convergent than just like oscillating, right? Like -1 to the n, totally divergent. It has like no reasonably like convergent behavior, basically. Okay, so maybe that's counterintuitive. In both of these cases, right? Oops. Oh, yeah. Wow. Okay, one more try. Yeah. So in both of these cases, we say the limit exists. But in both of these cases, we say the sequence diverges. Okay. So yeah, this case here is this weird like in-between thing where it still diverges, but the limit exists. Maybe confusing, pretty important to get straight as quickly as possible. Okay, so with that, let's just look at a couple. So there are just two theorems, it'll be pretty quick, that adapt the, yeah, let's just get rid of all this, that adapt the product and reciprocation rules for limits for situations where one of the sequences diverges to plus or minus infinity. Okay, so let's see. So the first one here would be, so this is theorem, I think 9.9. Right, yes. So suppose Sn diverges to positive infinity and Tn converges to a number T, which is greater than 0. Then Sn Tn also diverges to positive infinity. So this is basically the product theorem for sequences adapted to the situation where one of the sequences goes to positive infinity. This obviously also, you could prove this theorem when both of them go to positive infinity, or you could prove variance where this one goes to negative infinity and then this one goes to a positive number and the result would go to negative infinity. Or vice versa, this could go to positive infinity, this could go to a negative number, this would go to negative infinity, right? There's like, I think 8 different possibilities or something like that. It's really annoying to slog through, but we're only going to do one because all the proofs basically look the same with some, you know, plus or minus signs flipped around and maybe some inequalities flipped around. So yeah, okay, so let's think about, it's like the same structure, right? But instead of epsilon, right? Remember the game, the convergence game. In that game, it was like the devil would hand you epsilon and then you'd have to pick big N, right? But now capital M like plays the role of epsilon. So now instead we get handed M, you know, by the devil or whatever, right? Like, and M, it's probably going to be really big. It's going to make it challenging, right? So he's going to say like, all right, here's a really big number M. Show me that the sequence gets bigger than this huge number, right? So that's what we have to deal with. So let's just do it, right? So let M be greater, well, let M be a real number, right? Don't want to do the same thing the book's doing here. So let M be a real number. Now we just have to find capital N so that, capital N, sorry, so that the sequence SN/Tn stays greater than m. So we want SN/Tn to be greater than m. Okay? Now we can make Sn be really big because so that's what we're going to have to do, but we have to deal with Tn first, right? So basically the problem would be if Tn gets really small, that's going to be what makes it hard for us to make the product of these things be really big. So we want to try to control how small Tn can get, right? So to do that, we can try to put a lower bound on Tn, but we want that lower bound to be bigger than 0, right? That's the key. If we make a lower bound that's smaller than 0, it's useless. So luckily, we have that example that we've already used once, right? So by the previous example, the infima of all the Tn is greater than 0. So call that little m. I don't remember if that's what the book uses for it. Oh, yeah, they do. Nice. All right, cool. So then SN/Tn is greater than. Notice also that the absolute values are like nowhere to be seen here. That's because it actually matters whether this is positive or negative, because we're trying to specifically show it goes to positive infinity, not negative infinity, right? So we're not just showing that the absolute values go to infinity, we're specifically showing that the terms themselves go to infinity. And by the way, if you did show the absolute values go to infinity, that would not show that the sequence converges to positive or negative infinity. So maybe we'll come back. It's kind of a tricky thing. We'll come back to that. Okay, so SN/Tn is greater than Sn little m, right? So we want Sn little m to be bigger. So we should make Sn be bigger than m over little m, right? So pick n such that, so yeah, set m to be the infimum of these absolute values of Tn, which is greater than 0, right? Now pick n such that Sn is greater than m over little m for n greater than n, then SN/Tn greater than Sn little m, which is greater than m for n greater than n. And we're done. Okay? Pretty slick. Not too bad. Okay, one more. One more. This one is the reciprocal theorem. So yeah, of positive real numbers, then limit of Sn equals positive infinity if and only if the limit of 1 over Sn equals 0. Okay, pretty intuitive idea. Sorry, this should be a 10. So now notice, right, there's an if and only if here. So that means we have to go 2 directions, right? So let's first assume, so proof. Suppose limit of Sn equals infinity. Now we want to show that the limit of 1 over Sn equals 0. So what we really want, so let's let epsilon be greater than 0, and we want to get 1 over Sn less than epsilon. So we want 1 over Sn less than epsilon. But then this is the same as wanting Sn bigger than 1 over epsilon. So take n such that Sn is bigger than 1 over epsilon, right? You should be getting used to the flow of this now, right? So we're exploiting the fact that Sn approaches infinity, right? Positive infinity. That was our assumption. This is where we're using it, right? The fact that this n exists comes from that assumption. So now, so then for all, so this is for n greater, n greater than n. Then for all n greater than n, indeed, 1 over Sn, which by the way is also, you know, since all the Sn are positive, all the absolute values just go away in this entire proof. So we've done that part. Now suppose the limit, and it's just going to basically be a backwards version of this, but I'll write it out. Now suppose the limit of 1 over Sn equals 0. Let m be a real number, right? Then, so in this case, actually, right, let me think. We might actually want to assume m is greater than 0 here. Right. Let's just do that to be safe. We'll see how it works out. So we want Sn to be bigger than m. So that's the same as wanting 1 over Sn to be less than 1 over m. Right, yeah. So I had to take m bigger than 0 because otherwise if m was like 0 or smaller, this inequality wouldn't even make sense. But if m is bigger than 0, we can actually do this. And remember, like, it doesn't matter that I'm only doing it for m bigger than 0, because if m is 0 or less, then I can just pick a positive number anyway and make Sn be bigger than that, and then I've also made it be bigger than zero or any negative number. So it just doesn't matter. It doesn't matter that I'm only doing this for positive values of m. Okay, hopefully that makes sense. Yeah. So the fact that I can make Sn be bigger than positive values means I can also make it be bigger than 0 or negative values if I want, right? So so take capital N such that 1 over Sn is less than 1 over m for n bigger than capital N. Then Sn is bigger than m for these n. So that's it. Okay. So hopefully that wasn't too much of a slog. There were a lot of theorems in this lecture, but yeah, in the next lecture, we'll move into monotonic sequences, which is pretty cool. And I'll see you then.